because I always record. Now, you know what? I was having computer issues yesterday. Towards the end of class, people were telling me I was freezing up. And so actually wasn't able to post yesterday's lecture, which is no great loss. No great loss to pedagogy, let me tell you. But I will work on it again today to get it posted. That's yesterday's lecture. And then I will also work on getting today's lecture posted too. My computer seems to be really behaving very well today. It's taking pity on me. Yesterday, like I said, towards the end of class, people were complaining at me that that I was freezing up. I'm not really sure what that was about.
Yeah, in the ice tray, yeah.
Yeah, the ice tray, that's right.
Oh, sorry, my mic was on, sorry.
That's okay. I was, look. Nice. You know what? Sometimes you're teaching a class like this, you just have to tell jokes and laugh and get a round of applause and everything. So thanks for saying that. Anyway, but the screen was freezing and I'm not really sure what was going on, whether they were working on the internet down the block or who knows what. But everything seems to be moving relatively smoothly today. And really the big test is going to come in a few minutes. We'll try to see if my cabbage juice is colored correctly. Right, that's the big test we'll do in a few minutes. Okay, I've got brand new cabbage juice. You know, anyway, we'll get to that in a few minutes. I absolutely want to see how cursed we are today. Anyway, I'm hoping that we are going to do okay. So today's the 21st of July. Hard to believe, isn't it? I mean, I hardly go out, so I don't know what it's like out. I think it's probably pretty hot, and they're talking about storms and that kind of stuff. So I'm going to repeat something that I'm worried about. I can see the sky is gray outside, and I'm worried about storms happening and all that. If we are really close to the end of class, you know, a half hour, and for some reason the internet just crashes, then I'm probably not going to try and initiate a new meeting with a half hour left in class, okay? But if we are more than a half hour left and somehow the computer crashes, lightning strikes, whatever, I'm going to try and initiate a new class meeting that probably will require me to send you out a new link. So I just want to know that I'm going to try and get all the way to the end of class today without any electronical errors or whatever. I mean, only my errors, which those are profound, I know. But you know, if it starts storming out and you know the electricity or internet is weird, I'm going to try and reinstitute a class meeting unless we're in the last half hour of class. Okay. All right. Or we have basically called the class to an end. All right. So. Oh, I've got lots of exciting things to tell you. I really do. I don't even know where to start. It's so exciting. But here's one of the things I got to show you, because I'm going to go over here to home. Oh, by the way, let me just double check and make sure that everything's right. I'm recording, I'm presenting. Everybody can, I hope, see what I'm about to show you, okay? Because what I'm about to show you is how to get to MyPima or D2L, whichever you choose. Remember yesterday they changed things? They reconfigured things over the weekend. Well, here's what they did. They decided that almost everybody is not using the old MyPima format, you know, the MyPima homepage. And so that they were going to automatically default everybody to D2L. And that's fine if you are, in fact, somebody who's using the D2L format exclusively. And it does encourage me in the future to use the D2L format exclusively, to be honest with you. But in the interim, I like to post things, especially things like quizzes, on D2L and my Pima. All right, so let me show you how to do that, how to get back and forth. And hopefully it was really easy to me once they explained it to me, but I got to admit that, well, I'll show you what I mean. Look, so I'm going to go to my courses. All right, it's just loading, and there I am at my courses, okay? And there's my course. There's what you would click on or what I would click on to go to our courses. Now, over here to the left, I mean, I'm pointing at it right now with the cursor. I hope everybody can see it. There is the faintest icon in the history of icons, I think. I mean, I actually asked them yesterday in the tech support. I said, could they have made this any lighter? And I think they said no, they couldn't have made it any lighter. They made it as light as possible. I can barely see it. I mean, it is light gray on white. So anyway, there is actually a little icon here, or I don't know what to call it. They call it a toggle switch. So look what happens when you click on it. It offers you the opportunity to address your class in D2L, Pearson, I don't know what the heck that is, or my Pima. So if it's set in D2L, please wait. If it's set in D2L, then when you go here and you click on this, take a look. It's really not going to give you any options. It's going to go straight to D2L. And it sort of pretends that my Pima doesn't even exist anymore. Okay, that's fine, as long as you understand that process, which I barely do, but. Okay, so now I'm going to go back to my courses, and I'm going to look for the faintest icon ever. It's right here. I'm going to click on it, but I'm going to put my Pima instead. And I'm happy to wait, like it says, while it resets. Now take a look. You go over here and you click on this. It takes you to my Pima. Oh my gosh. Now, really not difficult, but you know, the bottom line is that it is a new tweak in the whole story. No one told me about it. I mean, again, they said, look, we think there's an email that's been sent out about this. I was like, okay, I don't remember seeing that email, but I get a lot of emails, and some of the emails are so long, it's crazy. So maybe it was buried at the bottom of an email. And P.S., by the way, we're going to do this. Yeah, I didn't catch it. But while we're here in the My Pima drive, let me show you that what's here now in the My Pima drive are some things that I would like you to look at today. Remember, this defaults to 20 documents. You don't want it at 20, you want it at 50. There's going to be 50 documents in here before too long. So look, I've got right here, keep going down, Steve. Oh, no, there it is. 0011 quiz 5. It's true, I posted quiz 5 today. As if you guys didn't have enough work to do. You've got the exam, you've got lab. Now I've posted quiz 5. I'm sorry for making your life this difficult, but I got to squeeze those quizzes in. So quiz 5 is posted there. And like always on these, I actually, as always, I'm pretty sure if I look back at any of these quizzes, I would see that there was a due date on them. So this is posted today. before class, 7/21. It is due by noon on 7/23, which is Thursday. So it's not due the same as the exam. You have a whole nother. So in my opinion, forget it. I'm going to work on that exam. I am not going to, I'm not going to worry about this until I'm done with the exam. That's what I would suggest.
Question.
So this first question that's here, it's identify the molecules of the carbohydrate. Which of molecules, big molecules of life it is? It should be. I'm going to close this out. Just you see it there. This is thought questions number 2, which hasn't been posted. I will refer to it today. So there we go. Then down at the bottom, way down here, I've got some documents that I'm not going to be able to have time to look at all these documents today, but cell theory, cell organelles, probably. Okay, and then the chemistry PowerPoint that's up here is not the most up-to-date one. So I'm going to read that, repost that after class, because who knows, I might end up we have to repost. No reason to repost it right. Did I just not delete? Oh, there it is. Let's make it. So you go to home. Some people are like, "Oh, this is much." You go to home. It's easier if you about it. Yes, it's not easy. Spring it on you over the weekend. Nobody tells you about it, and then it's 10 minutes before class, and you are unaware they've changed things around. Remember, it's fainted on in the history of iconography. Right? You click on it. You choose. Do I want to go to my Dwell homepage? Do I want to go to my Pima homepage? Again, I don't even know what Pearson is, but I don't have time to push on it. Okay. So. Man, I feel like a computer expert now. I'm explaining computer stuff. That's just hard to believe. Did you have any questions about that? Oh, chat line. I missed lots of chats. There's no button. I don't have that button. You mean you don't see that little icon? Well, I'm telling you, this is the faintest icon ever. I would never have noticed it was there.
Yeah, there is no little something at the side of ours.
There isn't. Oh my gosh, that's crazy. That is just crazy. I mean, and you go over there and you kind of hover cursor and you see anything.
Yeah, I'm getting the same thing. There's no gear button to change anything. I saw on your screen that it was on, that it showed up on the ones that's, so they say the same thing on mine. It says courses I'm attending and courses I'm teaching. Yours showed up under courses you're teaching.
Right.
Maybe you can set that there for the rest of us.
Oh, right.
Hoping.
Oh, maybe. Let's try it. Well, let's just see what happens. I'll that it. See, this is a completely different way to get to D2L. Right? There is a completely, I'll show you what I mean. And you can tell me whether you have the same, thing that I do. Because here's my here's the home page for me, right? And down here, I've got, it's resetting. Okay, so now I reset it to my Pima, okay? Homepage. And I'm gonna go down to here where, look, this is how I get to D2L. Is that how others get to D2L? You've got this like launch pad here where you can go to Gmail and all that. Is this not a student?
I think that's there for me too, but I just have a saved link to D2L's homepage.
D2L? What about somebody else, do you have this launch pad thing? I mean, does your page should look just like this? Right? Sit right down here. It has a launch pad where probably Gmail and some of these things that need to be done. But I've got a D2L link right there. So whenever I want to get to D2L, I go that way. Do other people have this? Other people have that sort of launch pad?
Yeah, I have like that.
Jump on.
I have like that. Yeah.
Exactly. Yeah. So we know having D2L is not an issue. What they could have put was one of these, go to my P. Now, I reset one to Pima. I'm not real confident that that's going to everything for everybody else, unfortunately. I wish I was confident about that. But, well, that's really interesting because, they walked me through this yesterday. And, yeah, that's my question. Some students can't do this. Okay, let's just solve computer problems during most of the class and put the biology off till tomorrow. I'm gonna see what I can find out about that and let you know about that as fast as possible. Because I am still posting things on my Pima. Oh, they told me, look, Steve, just stop posting stuff on my Pima, which I think in the future I'm gonna have to. Those same exact things that I posted there, I will post them on D2L too, okay? So I can post a Word doc. I can post that stuff on D2L, the new thought questions, et cetera, et cetera. Okay, well, you learn something new every day, and that's why we're in class. We're here to learn something new. Okay, so thanks for everybody for chatting at me and letting me know about this. That's crazy. I thought everybody, of course, would have that crazy little ultra faded link, and but I was wrong. Okay, so over here, wow, I got a lot of stuff I want to show you today for sure, but all right. Where was I going to go first? I guess I'm going to go here so I can figure out what's going on. The daily agenda. So, okay, let's start at the top. These thought questions are probably still pretty darn good, but look, I've added some new ones, A1.1 to A5, and those are part of thought question sheet number 2, which is here. Now, I haven't posted this yet. I apologize, but I'm going to post it as soon as we're done with class. So I'm making myself a note, post TQ2, brand new thought questions. Now, I don't know, these thought questions maybe, I used to think these thought questions were extremely useful in the context of a classroom teaching situation. I'm just not as convinced of that now. But I still think it's useful to point to some questions that I think were covered in class and that you should be able to look at. And of course, I do use these thought questions for, I'd use these thought questions on quizzes, etc. So anyway, brand new thought questions. And again, I'm going to post those. Oh, whoa. I'm going to put down right here. Well, Atoms and Molecules Lab, people have been turning it in to me. Thank you very much. I haven't even looked at it yet. Molecules of Life, just read it. The pH at Home Lab. Oh, wow. Okay. Let's think a minute about the pH at Home Lab, shall we? New cabbage juice. One thing I noticed about this cabbage juice is I think I might have left the water in yesterday's cabbage juice too long, and it was really dense, thick cabbage juice. This is not as dense, and that could make a difference, I think. Ew. I didn't refrigerate it, and it has a, I don't know. I don't know how a wine enthusiast would describe it. I would describe it as bordering on the gaseous emissions of humans. Right? Anyway, all right, so now, here's the crazy thing. I haven't done this yet. I mean, I should absolutely have done this before class, so if it just screws up, then I'm like, oh, great. No, but I've got it. It's got, I would say that let's just blow the light situation away. I guess I would describe this as kind of, I don't know, purplish, right? Purple cabbage, red cabbage. Okay, so now what I'm adding to it is I'm adding pure 100% vinegar, and I better find something to stir it around with. But I will tell you this, even to my feeble vision, look, the color has changed. I mean, it's changed to pink, something like that, something pinkish. Yeah, I would describe it as roughly pink. It has changed color, though. That is a wonderful thought. All right, so now I need to figure out where to dump this. I didn't think this through. I should have had a big, bucket to dump it in. Vinegar, no doubt about it. All right, so here comes some more. I'm just playing, right? It does make a difference how good your color vision is. But, all right, so this is the regular red cabbage again. Wish I had another light that I could shine through it from behind so we could get a actual color of it, but I don't. All right, so now talk about going to full range. Household, backwards, I'm sure, household ammonia. This is a nasty base, no doubt about it. And in fact, many people don't even have it around their house anymore. It says, eye irritant, keep out of reach of children. I don't know. I think on a bottle of ammonia, they should have one of those skull and crossbones because it's nasty stuff. If you drank this would be really bad. You don't even want to breathe this. All right, so now everybody's watching. Let's see what happens when I add household ammonia. Now it's like magic. Ooh, yummy. I'm only joking. That's household ammonia. Don't even get that on you. All right, so now what do you think? What color? Well, it depends on how the angle I hold it. Hey, look, even with my feeble color vision, and believe me, my color vision is kind of feeble. And somebody on the chat line, tell what color this looks like now. Remember, of course, what color it was.
It's like a bluish kind of on my screen.
Bluish? Anybody else? I've got like a little blue-green color blindness, but this looks pretty. Oh, you know what? Give me a second. Light behind it, does that make a difference? I think it does. Come on, somebody tell me what color it is, please. Maybe my computer is so bad that people can't even. Bluish? Okay, well then that must be my color vision. It looks really green to me. Or turquoise maybe. It looks greenish to me. Of course, that's too much light, but when I look right through it, it definitely looks greenish to me. So I'm going to mark that down as a success, that it actually changed color today. When I put vinegar in it, vinegar, of course, is acetic acid, therefore a pretty good acid. It changed red, right? And when I put a strong base in it, and I gotta go flush this down the toilet or something. I can't leave it sitting there. It turned green. So I'm really looking forward to seeing your pictures and the kind of things that you put in it. I think I left it sitting I let the water sit in the cabbage too long, and I made a too thick of a solution. I could have probably taken yesterday's solution and diluted it in half, and it would have made a great indicator. But the problem is it was so thick and so dense that you weren't able to really see the color well. I'll be right back. Sorry, I didn't want to take the chance that clumsy me, I would knock that over and it'd spill ammonia and cabbage juice and everything else. I mean, I've got animals, 4 cats and a dog and 2 humans that live here. And so this house has a cacophony of olfactory information in it. And I didn't want to add ammonia, vinegar, and cabbage juice to that by dumping it in the rug here in the studio. Anyway, hey, I think that I'm going to give the cabbage juice a round of applause because it seemed to actually work today. So, you know, if you are interested in pH, you could, of course, go online and buy a pH meter, and that would be not very expensive, as Kendall pointed out to us. But you can also go online. I'm freezing up. You can also go online and buy pH paper. It's called either Litmus, Litmus, or pH paper. And that will come in a little tube or in a little container. Sometimes it looks like a little matchbook. And there'll be a colored scale. And that colored scale will give you an indication. You dip it in. Yeah, just dip it in real quickly, take it out, compare it to the color scale. It is either called pH paper or litmus paper. And you can buy it online, no doubt about it. When I was a kid, you could go to a hardware store and they had like a chemistry section, believe it or not. I wish I'd taken a picture of that. And you could buy pH paper there, beakers, graduated cylinders, etc. And I saved my money. I would save my allowance up to buy scientific equipment like that, as opposed to baseball cards or comic books or whatever my peers were buying at that point in time. Though I was pretty peerless with a graduated cylinder instead of baseball cards. Okay, all right, so good. That was Dynamite. I came to that because I was looking at the agenda here. And then I'm just going to just leave this here for a second. You can look at it. I'm going to get those other lectures, that's 11 and 12, posted as quickly as I can. The basic chemistry 4 PowerPoint, we will finish that up in a few minutes today. Then quiz number 4 is posted and due noon. Whoops. This is the right day, but this quiz number 4 is old news. Sorry. I'm tweaking here. Old news. New news is exam 1. Whoops. Exam 1 was posted yesterday, July 20th, and it's due by noon tomorrow, July 22nd. So I really want to ask about the exam. Is there any questions I can answer about the exam? I guess really I've got the questions. Believe me, I've got plenty of questions. The question is, have people been successful at being able to complete the exam on D2L? Because look, I told you, this is the first exam I've ever written on D2L. So it's, believe me, if people came back to me and said, Steve, it is totally screwed up, I cannot answer the questions, I would be sad, but I wouldn't be surprised. So I haven't gotten any emails from people saying, Steve, I can't open the exam, I can't answer the exam. I haven't gotten any emails like that. Normally I would. But I'm asking right now, please, if there's anybody who's having issues or problems with the exam on D2L, I'd love to hear about it, because it's possible. There's a slight possibility I could correct it, fix it. But since people aren't just clamoring to tell me about problems, then I guess that means that it's working okay. All right, well, good. Enjoy it. Hey, look. I mean, I hate to say this, but I wish I was in a science class where I could take an exam and it would be open note, open book, and I had 48 hours to think about it. I mean, I don't know what to say. The COVID-19 virus, in my opinion, is forcing us to have, I don't know, just to institute some educational practices that are different. And what I mean is, look, I can't proctor your exam. We have no setup for proctoring exams. Oh, I can tell the exam to do things like move the questions around randomly for different students, but when you're giving people a window of time to work on an exam, you just, I don't know. I feel like I might as well make it open note, open book, because I could say to people, no open note, open book, and there would be no way to enforce that requirement. And there would be some students who would be very honorable and not even think about Googling anything. And then there would be students who would be like, well, 48 hours, I might as well make sure I get as good a grade as I can. I mean, I've been a student as long as anybody in this class, so I got to tell you, I know what it's like to be a student. So, open note, open book, 48 hours to work on it. I don't see why everybody doesn't get an A. And if in the end, at the end of the semester, I give away a lot of A's, well, fine. And if somebody comes and complains to me about it, I'm going to say, I'm going to blame it on COVID-19. I'm assuming that sooner or later, the scenario will be different. I mean, there was all these people optimistic on the news yesterday that they were this close to a vaccine. I mean, I watched a couple of nightly newses at night, and there was a lot of kind of happiness that we were this close to a vaccine. Of course, having a vaccine that works and then testing the vaccine, and then getting the vaccine made so that billions of people can take it. I mean, remember, there's 7 billion people on the planet Earth, 7.4 billion. I mean, in the US alone, there's 350 million, I think, give or take a million or two. So they'd have to get lots of doses of that vaccine made, and then they'd have to figure out how to do it. And I can just picture it in my mind. The lines, around Walgreens where they deliver the vaccine or something like that. Hundreds of people wrapped around Walgreens waiting to get the vaccine. And so that's, first they got to finish the vaccine, then they got to figure out how to deliver the vaccine. That's big and complicated. Then they got to start administering the vaccine. And I don't know, I mean, right now you go get your flu vaccine at CVS or Walgreens or Walmart or Circle K, whatever. And so I'm assuming they're going to do that same thing with this vaccine. I mean, if they make everybody make an appointment with their doctor and go there, all that might be a little bit more complicated, but it's still going to be a while before people get vaccinated. And then once you're vaccinated, you hope you have the appropriate immune response, and that response sticks with you, right? That you're immune to the virus thanks to the vaccine, and that you're immune to the virus in 6 months and in 10 months, etc. I mean, there's lots of variables in how well these things will work. But we're crossing our fingers and saying, pretty soon, who knows, within a year, maybe we'll get a vaccine that works and all that. And then everybody can go back to class. And assuming I haven't had a stroke from blood, my high blood pressure with the technology alone, then maybe I'll be back in a classroom. But anyway, what a pleasant conversation, huh? Let's see, what else did I want to show? I wanted to go back to the agenda real quickly. Okay. Quiz 5 will be posted Tuesday before class and due noon Thursday, 7/24. Already done. It's a done deal. It's already posted. I would wait, do the exam first, and then get to the quiz. But, a couple people have emailed me, said they took the exam, and it took them, an hour to take it. It's there on D2L waiting for me to grade it. I haven't gotten anywhere near it yet, but I will start getting to those as soon as possible. All right, so go ahead.
Steve, 7/24 is Friday.
Oh, 7/24 is Friday.
Friday.
So
quiz 5 will be Thursday, will be tomorrow.
Yeah. Hold on.
Wow, okay. 23.
Wait a minute. If quiz 5. Oh, well, yeah, I believe it's on Friday, but what did I say here? I said quiz 5 posted today before class and due noon Thursday, and noon Thursday is 7/23, right? And then exam 1 been posted already, and it's due tomorrow by noon. Okay. Did I say anything about 7/24? Are you just trying to see if I've completely lost my mind? Anyway, okay. I'm done with this. Again, though, I'm letting this sit here for a specific reason, because I don't actually post these. They're too flexible. And so if you want to copy down anything on here, I would copy it down. Like due dates and deadlines and all that. I'm on lecture 12. Whoops, darn it. On the wrong darn day. All right, I'm on lecture 12. I have posted lectures 1 through 10, but I haven't posted 11 and 12. I will work on that when we're done with class today, okay? All right. I'm going to leave this up so that anybody wants to write down deadlines, they can. What I miss is the people standing outside my door before a quiz. Everybody's all stressed out and fretting and worried about the quiz. And I open the door and there's just this incredible energy of fear and craziness. And I start handing the quiz out and people take the, boy, I miss the good old days when you actually dealt with a piece of paper. But no, not now. It's all electronic now. And so the world is now an electronic world. Okay, fine. No reason to complain about it. What do I got over here, here, here? Oh, gosh, I've got so many cool things to show you. I'm going to go here first. This is a document that is not posted yet. Oh, but believe me, it will be posted. And it's called Types of Chemical Reactions. It's one of those, hey, come on. Not going to let me zoom in. I wanted to zoom it a little bit. I guess it's sort of visible. It's pretty visible. Maybe it's just being slow. That possibility, I suppose it's just being slow and difficult. Surprise. Wow. Come on. Uh-oh, am I still here? Frozen. So I could see I was frozen up there. What's going on? But okay, I'm going to try and go back to that document. Right, well, I guess I'm not going to try and enlarge it, okay? I'm just going to go to it and show it to you. I closed the other side off, huh? Okay, I'll get it. Sorry, this is a document that I absolutely will post as soon as we're done today. It's called Types of Chemical Reactions. And it's based on the idea that, look, we've been looking at all these different chemical reactions and let me see if I can find it again. Okay. Hey, can everybody see this? You know what? I can't see the screen, so if somebody would please just say, Steve, I can see it. That would be wonderful.
I can see it.
Thank you. That's all I needed to hear. I can't see it, so I mean, I can see it, but I can't see anything else. It's just the way the computer's configured. All right, so this document, which is going to be posted on my PIMA and D2L, is called Types of Chemical Reactions. And I thought, you know what, we've been talking about chemical reactions again and again and again, and I wanted to organize that thinking just a little bit. So I created this document called Types of Chemical Reactions. So just to be sure we're all on the same page, here we are. Here's what chemical reactions tend to look like, right? They look like A plus B reacts to form AB. A plus B arrow AB, okay? On the arrow is important because the stuff that's on the left side of the arrow is called reactants. And the stuff that's on the right side of the arrow is called products. That's R stands for right, L stands for left. Left side, reactants. Right side, products. And so you could really read this way. Reactant A plus reactant B reacts to form product AB. Okay, so just so we have the terminology down, this is, you know, a standard form for a reaction. And the arrow gives us some information because generally on the left side of the arrow, we are dealing with the things that are going to react. And on the right side of the arrow, we're dealing with the things that have reacted. In this case, it looks to me like I've got a monomer and a monomer reacting together to form a polymer. It's a small polymer. Okay, so the first type of chemical reaction that I'd like to talk about is this one called the synthetic combination or anabolic reaction. Synthetic, I said this before, is a reaction. A synthesis reaction is where you take monomers and you hook them together to form a polymer. Combination is like, okay, we're combining the reactants to form a product. But my favorite word here is anabolic, because anabolic is the most biological of these terms. Anabolic means a reaction where monomers are hooked together to form polymers. It is a building reaction in the sense that you're taking small things and hooking them together to build larger things. Like in the PowerPoint yesterday, we talked about anabolic steroids. Steroid, of course, being a type of lipid hormone based on cholesterol, but it's pretty well known that if you take certain lipid hormones, anabolic steroids mean some kind of testosterone-related hormone, it will help you build muscles. So anabolic means building, and anabolic is a reaction where monomers are hooked together to form polymers. So that's the bottom line. Monomer A plus monomer B react to form polymer AB. AB is a bigger thing than either A or B. It's combined A and B together. Now, when we combine them together, of course, we form a covalent bond. That's how we combine them together. We don't weave them together or glue them together or something like that. We form a covalent bond with them. So here are some human examples. For example, there are humans that can take glucose monomers and galactose monomer and form lactose. This is a monosaccharide plus a monosaccharide reacting to form a disaccharide. Okay. Oh, what about this one? Glucose plus glucose plus glucose plus glucose plus a bunch of glucoses all hooked together to form glycogen or animal starch. This is a storage form of glucose that we humans put in our liver. When we have lots of glucose and we're secreting insulin, we are going to say, one of the things insulin will do is say to liver cells, hey, take in glucose and build glycogen. This is one we do all the time. We talked a little bit about it yesterday. We build proteins. Take amino acid, amino acid, amino acid, a whole bunch of amino acids and hook them together with peptide bonds to form a protein. What was the name of some proteins we talked about yesterday? Hemoglobin was one. Insulin, Titin, keratin, collagen, actin, myosin. So this is a super important reaction in every human cell, every second of our life. And then don't want to lose the lipids, right? Here's glycerol plus 3 fatty acids forms a triglyceride. 3 fatty acids, triglyceride. Now, for what it's worth, everybody noticed over here I put plus H2O, which means these reactions should really read like this. Glucose plus galactose reacts to form lactose plus water. Why why do I put water on the right side as a product here? And the answer is because this is a dehydration synthesis reaction. Remember how important dehydration synthesis reactions are? These are reactions where you hook 2 monomers together to form a polymer, and you do it where you have taken out a water molecule. So all of these actually are dehydration synthesis reactions. So one of the monomers has an OH, one of the monomers has an H. An enzyme, of course, an enzyme is going to be involved in this. It's going to splice off this OH and splice off this H and show the OH and the H to each other, and they are going to form good old HOH. That's H2O. That's water. Now, that means there's a free electron here on A and a free electron here on B, and the enzyme is going to show those to each other and form AB. So the bottom line is that this monomer A plus monomer B react to form polymer AB plus water is a perfect example of a dehydration synthesis reaction. And since there are thought questions that ask about these human reactions, let me make sure that I've included those thought questions on the thought question sheet, okay? On the agenda. So just give me 1 second to double check that. Questions I'm talking about are, I say, thank you for your patience. These must actually be on thought questions number 1. Here it comes. Yay, thank you, thought questions number 1. Zoom all the way down to here. Here it is right here, reaction types. And so actually Q, Q, Q through TTT. Q, Q, Q through TTT. Agenda. Okay, so make a note if you would. I just extended these to TTT, which means I'm including these questions. And one of the questions, I'm sure you caught it in the milliseconds I had that document up, that, uh-oh, I lost something here, didn't I? No. Here it is. In the milliseconds I had this up, I'm sure you caught that this had questions like, identify the 4 types of reactions and list 1 example of an anabolic reaction in human cells. So that's where that came from. And honestly, this almost finishes up thought questions sheet number 1, believe it or not. Okay. Well, people had a chance to get that down. I'll get thought questions 2 up today, posted today for sure at the end of class. All right, where was I? Agenda? No. Documents, there I am. Documents. There I am. Oh no, please. Be bigger. Don't be that big. All right, so dehydration synthesis reactions. The first kind of reaction is a synthetic combination or anabolic reaction. And you know, you wouldn't call this a synthetic combination anabolic reaction. You would call it either a synthetic reaction, or I would probably call it an anabolic reaction, because that's the most biological. All right, that one you're familiar with. This one, not so much. The second type of chemical reaction is called a decomposition, breakdown, or catabolic reaction. Decomposition, breakdown, or catabolic. Now, again, you wouldn't refer to this reaction as a decomposition, breakdown, catabolic. You refer to it as a decomposition, or breakdown, or catabolic. Now, the first reaction we talked about was called anabolic, a building reaction. This is catabolic, and it is a decomposition or breakdown reaction. And I don't know, in order for me to keep this organized in my head, it certainly does help that this starts with the word cat. Because let me tell you, in my house, cats don't build anything. All they do is break stuff down, right? So when I hear the word catabolic, I don't think about things being built up nicely. No, I think about things being shredded apart with claws, okay? Anyway, let's take a look at this reaction. Reactant AB reacts to form product A plus product B. Really, polymer AB reacts to form monomer A plus monomer B. I mean, you can see that this molecule here is bigger than these. This looks like the polymer. That's the arrow that says reaction. And then this looks like half of a polymer or part of a polymer. It is monomer A plus monomer B. So polymer AB reacts to form monomer A plus monomer B. All right. So again, let me give you some human examples. Lactose can be broken down into glucose and galactose. Talked a little bit about this yesterday, and we talked about the enzyme lactase. And if I had to, I'd write that enzyme right up here, lactase, to suggest that lactose isn't going to just naturally break down into glucose and galactose. It's going to need to be broken down in the presence of lactase. And lactase is an intestinal enzyme, so that's where you're going to get it. It's going to have to go through your mouth. It's not going to be digested in your mouth. It's going to go through your stomach. It's not going to be digested in your stomach. It's going to start being digested in your small intestine. And again, if you can't digest it in your small intestine, then that can cause some gastrointestinal issues, problems, challenges. Because if you can't digest the lactose, it's going to hinder the movement of water out of your gut, which means water is going to linger in your gut. And as it lingers in your gut, it's going to cause your gut to swell up and feel bloated and feel heavy, and also ultimately could result in diarrhea. If also, once it gets into your large intestine, there are bacteria there that are just happy to digest it, but when they digest it, they make intestinal gases. And again, those can cause pain and swelling and embarrassment, etc. So what do we do these days? Well, if you are lactose intolerant, you can go buy Lactaid. It's in the PowerPoint down there at Walgreens or Safeway or whatever, and you can add that to your food, and it is an enzyme that will help you break down the lactose into glucose or galactose. Oh, sucrose. We can break sucrose into glucose and fructose. When you eat sucrose, it gets broken into glucose and fructose. When you break a protein apart, you break it into amino acids. I've underlined the S here for a reason, because you don't break a protein into an amino acid. No, amino acids are the building blocks of protein. So let's say you even have a small protein like insulin that's 51 amino acids long. When you tear it apart, it's going to be 51 amino acids. That's why I underline the S. Glycogen in our liver broken down into many glucoses, right? Into many glucoses. So I want you to notice something here. I actually have water here as a reactant. So technically it should read water plus lactose reacts to form glucose plus galactose. Water plus sucrose reacts to form glucose plus fructose. And the reason is that this example of a reaction is called a hydrolysis reaction, or you could pronounce it hydrolysis. But this word root lysis means to split or cut, right? It means to split or cut. And so this is literally saying water is split or cut to make this reaction happen. And it's true. You know, when you have a polymer like this, where am I? When you have a polymer like this, let's just say it's two pieces hooked together, and then you pull them apart, an enzyme will do that. Well, one thing that could happen is if you hesitate, they could just go back together again, right? I mean, they're hooked together by electrons. So, what if you were to put these in an enzyme, like we looked at that enzyme yesterday, sucrase, and you broke them apart, and they're just sitting here like this? Well, if you don't do something, they could go right back together again. Oops, I can't even hit my own fingers. They go right back together again. And that's not what you want. You want them to come apart and stay apart. So one of the things you could do to make sure when they come apart that they stay apart is you could also break apart a water molecule and put the H here, so now this electron's not free anymore, and put the OH here, and so now this electron's not free anymore. And so now there's no chance they're going to come back together. So when we do a hydrolysis reaction, a hydrolysis reaction, we're doing a reaction where you break a polymer in half into monomers, but you also break water molecules in half so that you have an H and an OH that you can hook on those free electrons. Because, again, if you've got a polymer like this and you tear it apart, why doesn't it just go back together again? An enzyme doesn't want that to happen. So when an enzyme pulls it apart, it will put an OH here and put an H here, and now they are separate molecules, right? Okay. Thanks for bearing with my beautiful demonstration there. Oh, why does it do that? It insists on resetting itself. All right, so here's where we were. All of these are polymers that get broken down into monomers. In order to keep the monomers separate from each other, you need to break down water and insert parts of a water, that means the H or the OH, into the product. So here's your polymer to begin with, polymer AB. Here's water, HOH. We're going to split this water apart at the same time as we split this polymer apart. And we're going to put the H over here and the OH over here. And now the electron there that was free and the electron there that was free, well, they could, I suppose, have come back together, but no, they are not allowed to because a piece of a water molecule has been set inside of them. You know, just so that if you look at this list here and you think about this list for a minute, you may realize that what this sounds like is digestive reactions, right? We're taking lactose we ate, broken into glucose and galactose. Those can move across our intestinal cells and go into our bloodstream and go over to our liver, where our liver will, use the glucose to do something with it. It will modify the galactose into glucose, and whatever it can't use, it'll just throw it away. Sucrose, that's white table sugar. We put that on our grapefruit. It breaks into glucose and fructose, one of each together. Proteins are broken down into amino acids, and those amino acids are moved in the bloodstream, and then they are rearranged into other proteins. I mean, you eat cow protein, and you tear it down into building blocks, amino acids, and then you hook them back together in the correct order for the primary structure of human proteins. Okay, all of these are breakdown reactions that are also what I would refer to as digestion reactions. And there's a name for all those enzymes that do hydrolysis. They're called hydrolases, right? There's the enzyme, ACE. Hydrolases are digestive enzymes. And, you know, enzymes are very specific. So when it comes to digestion, there's no all-purpose enzyme. There's sucrase that digests sucrose. There's lactase that digests lactose. There's lipases that digest lipids. There's proteases that digest proteins. Peptidases that digest proteins. There's nucleases, ribonucleases that digest DNA and RNA. So the bottom line is that there's a whole bunch of different enzymes collectively referred to as hydrolases because these are digestive enzymes that we will use to break down our food. I mean, look, our food comes into our mouth mostly as polymers. And these polymers are way too big to go across the walls of the intestine into our bloodstream. So they have to be broken into monomers so they can be moved as monomers into the blood supply for the liver so they can be looked at. There's only one exception, of course, to that, and that's that is fats, which they don't break down super well. They don't travel super well in blood, which has got a lot of water in it. So they have to be carried by the lymphatic system. And I'm sorry to say that when you eat triglycerides, you will break them into glycerol and fatty acids in your intestine. Then you'll absorb the fatty acids, saturated or unsaturated, in your blood into your lymphatic system. And then you will dump those fatty acids, saturated or unsaturated, bang, right into your heart. So your heart gets to see those fatty acids before other organs do. Most other nutrients, sugars, proteins, and even nucleotides, they get examined by your liver first. Once they're examined by your liver, they get sorted. But not true of triglycerides. And I think the fundamental answer is they don't dissolve well in blood. So they go in the lymphatic system, they get pumped up and dumped right in the heart. Now they get mixed with blood, really mixed with blood. But that means that the first organ in your body that's going to see fatty acids is your heart. And if you're eating saturated fatty acids and they are going to turn solid at body temperature, I'm thinking it's your heart that's going to be going to get the first chance to see those. Okay? If you're eating unsaturated fatty acids that are liquid at body temperature, well, then those are not going to settle out in your heart or in your blood vessels and block them. And in fact, eating unsaturated fatty acids can help keep saturated fatty acids in solution and moving around a little bit better. Okay? So before I take a break, which I need to take a break and get up and stretch for sure, can I answer any questions anybody has about these chemical reactions, the first two that we're talking about? We'll talk about the other two when we get back. Am I going to post this on D2L? Yes, you bet I am. Of course I am. Because honestly, I think this is something you're going to want to print out and put right up where you can see it all the time. Anyway, any questions on this side? Move this to the wrong place. Should have it over here blocking my face. Okay. No questions?
Wait, is that under assignments?
No, this is just a document. It's going to be posted. It's not posted yet. It's going to be posted under the table of contents in the document list.
Okay, thank you.
And I will also post it on my PIMA after some of the other stuff that I'm going to show you today. You bet. But now that isn't very helpful though, because people are still having trouble getting to my PIMA, and I need to call them as soon as we're done with class and go, hey, why can't students access this? my Pima, toggle switch like I can. Anyway, we're going to figure all that out. Here's the break music. So, okay, break. Please do me a favor. Get up, stretch, move around, do 100 push-ups or sit-ups or something just to get your blood moving and, get some more caffeine or whatever it takes. All right? All right, I'll see you in 10 minutes. All right, I'm back. I'm wondering if anybody, I'm just curious about this. Did anybody see whether me toggling it over to my Pima made a difference for you? I mean, what that would require is you to go to my courses and just see whether it automatically defaults to D2L. And so I don't know, when somebody gets a chance, check that out. I mean, it seems crazy to me, of course, that I have that little toggle switch that lets me choose to go to D2L or to my Pima, but you don't. None of this makes any sense to me. Just adding it to a long list of things, though, that don't make any sense to me about the universe at large now, right? So it does. It still goes straight to D2L. Thank you, Thelma. It goes straight to D2L. It doesn't, even though I toggled it over to my Pima, it still goes straight to D2L. I'm sorry about that. Well, like I said, I wrote myself a note to try and get some advice about this later today, and so I can get back to you about it. Because what good is it for me to post things on my Pima if you can't get to my Pima? I mean, I don't want to say I'm posting it in my Pima, and then people are like, thanks, Steve, but I can't get anywhere near it. All right, I forgot my glasses. I'll be right back. Okay, my computer glasses make it a little easier for me to work. So type of chemical reactions, here we go. We've already looked at this whole page, but I would love to answer questions about it if somebody has any questions about it. Well, if you think of a question, you of course know who to ask the question of. Got the second side, the other side of that page is, where is it? There it is. Nope, wrong one. There it is. There's the back side of this same document, a document I normally would just hand it to you in class. All right, this is the back side. This is the third type of reaction called an exchange reaction. Remember, the first one was an anabolic reaction, meaning a building reaction. The second was a catabolic reaction, which means a breakdown reaction. This is an exchange reaction. And let me just make a note here. This is mostly an ionic reaction. There's no monomer-polymer connection here. When I say ionic, I mean, we're probably not dealing with covalent bonds. We're dealing with ionic bonds. And this RXN is shorthand for reaction. So take a look at what it looks like. It looks like this. Reactant AB plus reactant CD react to form product AD plus product BC. So what has happened here is some kind of exchange, right? Exchange in this reaction. A and B came to this party together. C and D came to this party together, but there was some kind of reaction happening, and now A and D are together and B and C are together. It kind of makes me wonder what kind of party this is. Anyway, no, it's a reaction. It's an exchange reaction where pieces are exchanged. Again, this does not look covalent to me at all. This is a mostly ionic reaction. Are these big and these little? No, no monomer-polymer connection. And you know what? You already know about this reaction because these are examples of acid-base reactions. So give a perfect example. 2 molecules of hydrochloric acid plus 1 molecule of magnesium hydroxide. Do you remember what magnesium hydroxide is? Milk of magnesia. Okay. Hydrochloric acid is a pretty strong acid. Milk of magnesia or magnesium hydroxide is a weak base. You hook them, you expose them to each other, and you get a salt and water, of course. That's what you always get when you mix acids and bases together. But the point is that hydrogen ions here that are part of the hydrochloric acid or dissociated from the hydrochloric acid, they are going to be attracted to hydroxide ions, and they're going to bond together to form water, and water will then switch from an ionic bond to a covalent bond. You have nice, mostly covalent water. The hydrogen ions, which were tearing up your gut, well, your esophagus, they are now part of water, and their ability to irritate things is much less, right? I mean, why would you consider drinking milk of magnesia? It's not the most pleasant stuff to drink. It's because you have heartburn, your esophagus is burning, and it's because there's too many hydrogen ions, and you want to do whatever it takes to get those hydrogen ions to be part of a water molecule so they're not irritating the lining of your esophagus. Now, this is absolutely a human reaction. I put a star right next to it. This is not. This is a crazy reaction. This is sulfuric acid, that's battery acid, plus sodium hydroxide, that's lye. Nasty, 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 reacts to form sodium sulfate, that's the salt, and water. The hydrogen ions that were released by this sulfuric acid and the hydroxide ions that were released by this sodium hydroxide, they have come together and formed water. So the hydrogen ions and hydroxide ions have been essentially converted into water molecules. I mean, they've been chemically combined to form a water molecule. So what do you get? Acid plus base gives water plus salt. So this is the salt you get, sodium sulfate. And I don't know anything about sodium sulfate, but I do know this. You would never put it in a salt shaker, and you'd never put it on your cheeseburger or fries. It's just, these are pretty nasty chemicals. You wouldn't, this isn't a human reaction, so to speak. So an exchange reaction, the best examples of an exchange reaction are acid-base reactions. No monomer polymers, just plain old, no monomer polymer connection, ionic reactions. Last reaction in the 4 different types of reactions is a reversible reaction. And I'll tell you, you can immediately tell a reversible reaction if you look here at the arrow and you notice something bizarre. The arrow goes in both directions. What this arrow basically is saying is reactant A plus reactant B combine to form product AB, but product AB falls apart to form, reactant AB falls apart to form product B plus product A. This reaction will go in either direction. Sometimes the arrow is written like this, sometimes it's written like this. Bottom line is, though, is that this is a reaction that can go in both directions. So why does it decide to go in one direction or the other? And honestly, the reason it goes to the left or to the right has to probably do with 2 main things. One are the conditions that the reaction is happening in, because environmental conditions can make the reaction go to the right, to the left. Secondly, enzymes. Okay, remember enzymes, and by the way, there's a definition for enzymes down here at the bottom of the page. It says, enzymes are protein catalysts that organize and regulate all the important reactions of metabolism. So enzymes are proteins, you knew that. They're a type of, they form a 3-dimensional protein with very specific shape, and that is a catalyst that makes reactions happen faster with less energy when the cell needs them to happen. So just for the record, the other thing that could make a decision about whether this reaction is going to go to the right or the left has to do with enzymes too. So I don't know, this may seem like a crazy example, but I think it's an interesting example. And I call this reaction the soda reaction, and it absolutely has to do with good old soda, one of my favorite substances. Just going to look at the chat line. Okay, I don't see anything new, right? But bottom line, need this a teensy bit bigger. It would be nice. There we go. Reversible reaction, and we're looking at what I'm referring to as the soda reaction. So just bear with me while I tell you about this. I think a lot about soda. If you're in the soda making business, then you want to get some good, clean water. You want to cool it down so it's really cold, not frozen, that wouldn't be good, but really, really cold. And then, whoops, then you want to put it under pressure if you can and bubble carbon dioxide in it. If you bubble carbon dioxide into water, it carbonates the water, meaning some of the carbon dioxide dissolves in the water, and it will form an acid. So the arrow's pointing this way. It will form this pretty famous acid called carbonic acid, right? Carbonic acid. And that is H2CO3. Everything's accounted for. H2CO3 or carbonic acid. Oh, I'm so tempted to grab one of those, a little bit of that cabbage juice and put a straw in it and blow carbon dioxide into it and see if it makes a difference. I mean, remember, carbon dioxide, when you mix it with water, will form an acid. So I don't know. That's a future experiment that would be very interesting to do. The acid's H2CO3 carbonic acid. Now, if the water is still cold and is still under pressure, then a lot of that carbonic acid is going to dissociate. And when it dissociates, it's going to form good old hydrogen ions and bicarbonate ions. Hydrogens and bicarbonates. And you know what? We're talking about soda here. Those hydrogen ions and bicarbonate ions, those are an essential part of the flavor of soda. So I have to tell you that when I drink soda, I want it cold. I put it on ice to keep it cold. I keep the cans in the refrigerator. I mean, I try to keep it as cold as possible, because when it's cold, the reaction tends to go this way. When it's cold and under pressure, the reaction goes this way. We go from water and carbon dioxide to carbonic acid to hydrogen ions and bicarbonate ions, both of which are part of the yummy flavor of soda. They're part of the flavor. I mean, it's like if you just drink plain carbonated water, it has a unique flavor that's related to the carbonation. Okay, so that's great. I want to open my can of soda. I want it to be freezing cold. And when I open it, I'm going to be about to ingest delicious soda that has a lot of hydrogen ions, bicarbonate ions, soda flavoring, etc., etc. That's it. But you probably know this about soda. I certainly do. The minute I open it, I depressurize it. And the minute I open it, it starts to get exposed to my hands, to my lips, to the external environment, and it starts warming up. Well, as it warms up, this reaction wants to go this way. Remember, cold and pressurized, it goes to the right. Warming and depressurized, it's going to go to the left. So these bicarbonate and hydrogen ions will recombine together to form carbonic acid, and the carbonic acid will actually break apart into carbon dioxide and water. And when you taste that soda, it is disgusting, right? I mean, a huge difference in flavor. It's flat soda. The carbon dioxide has bubbled out. It's warmed up, and now it is disgusting soda. So the environmental conditions here are important. If it's cold and it's under pressure, the reaction is going to tend to go this way to make the yummiest soda combinations. But if the reaction starts to go this way because it's warm and it's depressurized, then what will result in is carbon dioxide bubbling out of the soda, and the soda not tasting the same because the bicarbonate ions and the hydrogen ions are gone. And that is a part of the flavor of a typical soda, is that those bicarbonate ions and hydrogen ions. So the important thing is, look at this, double-headed arrow, double-headed arrow. It can go this way or it can go this way. Whether it goes this way or this way depends on certain environmental conditions, for sure. Now, that's not a very famous biological reaction, though actually it is, because it turns out that every cell of our body is making CO2 every second of our life. And it's dumping that CO2 into our blood, and that CO2 is mixing with water in the blood, and one of the things it's doing is making carbonic acid, which will dissociate into hydrogens and bicarbonates, and that could affect the pH of areas of the body. So that could be a potential problem. But there's buffer systems involved that help make that not happen. Or not, maybe the word not happen isn't right. It helps make it have less impact on the pH. So let's look at a more biological reaction, one of my favorite reactions in the cell. It's called the ATP discharge-recharge reaction. And we're going to talk about ATP in a few minutes. ATP is often known as the #1 energy storage battery of the cell. Most machines in the cell are designed to run on this monomer nucleotide molecule called ATP. Glucose, of course, has tons of energy in it. It has too much energy. You can't run cell machines on glucose. They're just way too much energy. I mean, it's been compared to like, oh, I don't know, jet fuel or something like that, right? Jet fuel. And you just can't. You can't run most cell machines on it. You have to take the energy out of glucose, which you will be able to do, and transfer it in mitochondria in the cell to ATPs. And it's true that there's about 80 ATPs worth of energy in a glucose molecule. About 80 ATPs worth of energy. Now, we, at our best, can only extract about 38 ATPs out of a glucose molecule. It's not that easy to extract energy and transfer it. And so we can extract about 38 ATPs out of a glucose molecule and use those ATPs to do the kind of things we need them to do. So I'm going to show you ATP in a few minutes, but let's just start over here and say, look, here's ATP. This ATP here is the charged up, energy-rich form of ATP. It has adenosine and 1, 2, 3 of these things called phosphate group. And a phosphate group can bind to another phosphate group by a high energy bond. And so what's going to happen here is that when you have access to energy, you are going to use it to make ATPs, and you're going to use it to make high energy bonds. And ATP, again, will be used all over the body to do lots of different things at a cellular level, I should say, in cells of the body. Okay. All right. So this is the charged form. If you need energy, then you can rip ATP apart. Okay. The arrow, I'm going this way now. I'm following this arrow. And when you rip it apart, energy will spill out. Yay, we wanted that energy. It doesn't say where that energy is going to go. But then that energy was stored right in here in a covalent bond between this phosphate group and this phosphate group. So it's kind of like you grabbed this phosphate group and just ripped it off, and at least a portion of the energy that was in here, right, in this high energy bond would be released. And then you could use that energy to do something important in the cell, like move the cell around or break molecules apart or put molecules together. You know, when you do anabolic or catabolic reactions, it takes energy to make those happen. And we do thousands of those kind of reactions every day. All right, but once you've ripped this off, what do you have left? Well, you have that phosphate. Here it is, the one you took off. And then you have what's called adenosine diphosphate. Because this is called adenosine triphosphate because it has adenine, ribose, 1, 2, 3, that's monoditriphosphate groups. And anyway, when we rip the one phosphate group off, we end up converting the molecule to ADP, adenosine diphosphate, and a phosphate group. So if you need energy, you can take it out of ATP and use it for whatever the body needs it for. But if you have energy, if energy just appeared, I mean, let's say you ate a big lunch. Now there's lots of glucose in your cells. Your glucose starts breaking, those cells, start breaking that glucose down. Well, energy is going to appear. And if energy starts appearing like this, well, it would be foolish to not try and store it. And one of the ways you could store it is to take this molecule plus this molecule and reattach them together using this energy. So this energy is going to go into connecting this phosphate here, that's this one, to this phosphate here, that's this one, to form a high energy bond right here. Now, why would a cell do that? I mean, if a cell sees energy and it goes, well, I think I see a bunch of energy, I guess I'll just take it and store it in ATP. Well, it's because, again, I said, when you run cellular machinery, you generally run them on ATPs. You can't run them on glucoses. You can't run them on other energy-rich molecules. You need to run them mostly on ATPs. So if you have energy, you're going to take ADPs, that's this part, plus a P, and you're going to use that energy to hook them together and form ATP. Pretty straightforward, right? It's like reactant plus product plus energy, reactant plus energy reacts to form product, ATP, and now this phosphate group is attached to that phosphate group, and the energy that it got to do that is from the energy that's liberated here. You know, here's the thing about energy. If energy appears, then you really only have 3 things that you can do with it, right? If the energy appears, there's only 3 things you can do with it, as far as I can tell. Believe me, I'd be happy to be enlightened about this. If energy appears, then you can either use it immediately, or you can store it if you have it set up to store it, or 3 is you can lose it. Use it, store it, lose it. Lose it, store it, use it. That's what's going to happen. I mean, my favorite, I don't know if I have a match here, but a match is always nice when you're talking about energy, because you strike a match and you see that energy appearing, light and heat and all that, and then you have to ask yourself, well, what am I going to do with this energy? Well, maybe I'm just going to transfer the energy to the wick of a candle and start another chemical reaction, right? Maybe I'm gonna just let it burn out in a second, which it normally does. It's just gonna burn out and the energy is gonna be gone. Remember, when energy appears, you either store it, use it, or lose it. So cells are wise. They don't try and waste energy. There's only so much to go around. Okay, two additional types of reactions here, the exchange reaction and the reversible reaction. Could I ask And I answer any questions about any of these? There's the 4 reaction types. You know, I remember these by the word race, right? Reversible, anabolic, catabolic, exchange, race. Oh, better chat that up, huh?
Is it race? Did you say race?
Race, R-A-C-E. I'm writing it down.
Okay.
So RACE stands for reversible plus anabolic plus catabolic plus exchange. I used to think of it as ACER, was anabolic, catabolic, exchange, and reversible, but this one works just as well. If you want to remember those 4 kinds of reactions, which of course you do want to remember those for the rest of your life, okay? Did I lose them? Did I lose that document? Where is it? Oh, here? Yeah. All right, so I've got the chat up if anybody wants me to answer any questions about it. We're going to talk about the ATP discharge recharge reaction again in a few minutes. I couldn't resist a little leftover piece of paper down at the bottom. I wanted to give you a definition. The definition of it is for what is called a biochemical pathway. A biochemical pathway is a series of product-linked reactions organized by enzymes. Asterisk. Well, here's the definition for enzymes. Enzymes are protein catalysts that organize and regulate all of the important reactions of metabolism. It's true. I mean, I always hear that within cells, that individual cells have the capability to do about 30, well, I'm going to be careful here, to do at least 10,000 different chemical reactions as part of their normal life. 10,000 different chemical reactions. Well, there is going to be about 10. Did I spell it wrong? Thank you. It is spelled catabolic. Sorry. Thanks for catching that. Thanks. So it is catabolic, you know, breakdown reaction. Biochemical pathways. I was thinking about a biochemical pathway. A biochemical pathway, a series, which means several, of product-linked reactions organized by enzymes. So here's what a biochemical pathway looks like. Reactant A plus reactant B react to form product AB. Then product AB, in this case, becomes a reactant in the next reaction, which is reactant AB plus reactant CD reacts to form product ABCD. And again, this product ABCD becomes a reactant in the next reaction. So reactant ABCD plus reactant EF reacts to form product ABCDF. What I want you to notice about this is, look, you have to do this reaction before you can do this reaction. And you have to do this reaction before you can do this reaction. I mean, if there were 100 steps in this biochemical pathway, you would have to do every one to get to the final results. But the bottom line is that, do you notice that the product of this reaction becomes a reactant in the next reaction? The product of this reaction ABCD becomes a reactant in the next one. That's what they mean by product linked. Product linked. You can't do this reaction. Sorry, you can't do this reaction or this reaction until you've done this reaction. They're linked together in a biochemical pathway. And there's a number of biochemical pathways we need to at least mention and talk a little bit about. Over here on the right are the names of enzymes, right? Lactose is broken into glucose and galactose by lactase. Proteins are broken into amino acids by proteases. Triglycerides are broken into glycerol and 3 fatty acids by a lipase, lipid enzyme. Protein polymerase, well, polymerase builds proteins. So it takes amino acids and hooks them together to make proteins. And DNA nucleotides, we'll talk about those, they are hooked together by a very famous enzyme, DNA polymerase, that makes the DNA long chain of DNA molecules by using them. Okay? 4 types of chemical reactions. Okay? And questions related to those will certainly be appearing somewhere soon. Any questions about these last two or about a biochemical pathway or any of that? I'm so happy people will mute their microphones so I don't hear them actually snoring. Because I know that there are definitely people who are just asleep. It's hot. It's hot in this room. It's like 85 degrees. It's the middle of the afternoon. I mean, right now I want to take a nap, right? So believe me, all it would take would be somebody droning at me about chemical reactions, and I would start to lose consciousness. So wake up. It's time for class. Okay. All right, now where am I going to go? Well, too early to take a break, so I'm going to go here. I'm going to go to the Chemistry 4 PowerPoint. We're going to finish this Chemistry 4 PowerPoint as quickly as we possibly can. You know, I just want to overlap a tiny bit yesterday because kind of booming through everything yesterday. We talked about the enzyme cycle. We talked about proteins and what they do. We talked about the enzyme cycle because, honestly, one of the best examples of what proteins do in our body is enzymes. Oh my gosh, I don't know. This AIP industrial strength live bacteria enzyme solution, you know, I feel like I've used this before because I do, as I said, have animals. And when you have animals, well, part of that package is dealing with urine and feces and just general and hairballs and puke of various kinds. Anyway, all the fun things that people have animals for. But this stuff always kind of amazes me because it's not the only substance that basically tells you it has enzymes in it to help digest urine, digest feces, etc. Right? It is common for there to be pet cleaning products that contain enzymes of one type or another. Anyway, so enzymes are super important. We start to think about proteins. We looked at the enzyme cycle. We talked about amino acids, the building blocks of proteins. And I named some. Somehow I managed to stick another example of the enzyme cycle here, though this is identical to the last one, actually. This is the reaction where sucrose is broken into glucose and fructose. Water certainly has something to do with that. So the real bottom line is this is actually a hydrolysis reaction because water gets split up and pieces of the water molecule get put into the glucose and the fructose to keep them apart so they don't fall right back together again. Okay. Sucrose, broken apart by sucrase, into glucose and fructose. We looked at amino acid structure, how every amino acid has a central carbon and this thing called an amino group bond, NH2. This is the amino portion of the amino acid. Then it always has this acid or carboxyl group. There's the acid portion of the amino acid, amino acid, amino acid. That central carbon is always attached to one hydrogen. So really, if you just ignore the R, you see that every amino acid has a hydrogen, an acid group, and an amino group. But then there's one more bond there. The R stands for variable group here, and there's lots of different things you could put in there. The simplest thing you could put in there is a hydrogen. There's tons of hydrogens in the universe. They're plenty reactive. You could just put a hydrogen in there. And if you did, you would form glycine. Glycine being one of the, it being, I think, the simplest amino acid. Okay, glycine. We'll look at it. So we changed the R groups, and that affects the behavior of the amino acids. Some amino acids dissolve well in water. Some amino acids don't. Some amino acids form hydrogen bonds. Some amino acids don't. I mean, if you're very non-polar, then you're not going to make hydrogen bonds. But if you're really polar, then there's a chance you will form hydrogen bonds. Here's the 20 amino acids used to build human proteins. You don't need to know any of these really. I mean, again, it could be potentially useful to know glycine, because glycine's so simple. There's that central carbon. There's the obligatory hydrogen. There's the amino group. Here's the acid group, amino acid, amino acid. And then attached down here in the R position is just a lonely little hydrogen, most common element in the universe, and an element that likes to form covalent bonds for sure with carbons. The rest of them more complex. Okay, I did say the other day that there were 8 of them were essential, which means you need to get them in your diet. We talked about the dehydration synthesis reaction that takes amino acids and hook them together to make proteins. A dipeptide is the smallest protein you could make. Tripeptides are bigger, quadrupeptides, quadra must be septa, hexa. Oh, anyway, there's lots of, you can attach lots of amino acids together, thousands, and you do so using a peptide bond. So proteins are made from amino acids linked together by peptide bonds. The diversity of proteins is based on different arrangements of a common set of 20 amino acid monomers. Remember, each amino acid contains an amino group or carboxyl group. Also called an acid group. It contains one of 20 different R groups that fit in that one area. Here we go, carboxyl group. And so you've got 20 different functional groups to choose from. Okay. 3 groups and a hydrogen atom are bonded to a central carbon. Protein, well, I showed you a protein Titan that's 34,000 amino acids long. So certainly it can be over 1,000 amino acids long easily. You might remember hemoglobin was 146 amino acids long. Are these amino acids hydrophobic or hydrophilic? Real quickly, the way we made that decision was based on this R group, right? This is these are like methyl groups. This says non-polar. Probably doesn't dissolve in water as a result. OH and OH and O, these are probably, because they've got those oxygens, they're a little bit of an electron hog, and carbon's going to suffer because of that. So those What did I say there? These are going to be, this is going to be pretty polar and dissolve in water, so it'd be hydrophilic. Protein structure, we talked about it. One of the important concepts with protein structure is this one. The sequence of amino acids is called the primary structure of protein. Once you put together that string, it's going to fold into a unique shape based on the side chains present in amino acids. Hydrogen bonds create the shape, and the shape of the protein determines its function. It looks like I combined two sentences together here. So hydrogen bonds, again, super important in protein structure. And then we zoomed. Look at what the primary structure looked like. I mean, here's a piece of a protein, and here's the primary structure. It's every important part of the protein. So leucine, asparagine, alanine, valine, arginine, glycine, serine. I mean, we don't know immediately looking at these what particular protein is being formed here, but we've hooked these together in a very careful and specific way. This primary structure is very careful and specific. So you start out by putting all the amino acids together in the right order. In the right order. Even one amino acid out of order can be a problem. And one of the things that will happen is we'll start to form what's called an alpha helix. It's a helix like a slinky. It's held together by hydrogen bonds. Or we'll form a beta-pleated sheet, which is like a folded piece of paper that has, that again is designed to hook together and form a three-dimensional structure inside of the protein. When you have these, this is primary structure, this is secondary structure, and when you start to take these and put them together into some other living device, now you're talking tertiary folding, and then there's even a level beyond that, where you get these big blobs hooking together to form bigger and bigger blobs. All right, so the shape of a protein determines its function, no doubt about it. If you, this is good old form follows function. So hemoglobin, we went through this pretty quickly because I wanted to show you how the difference between good hemoglobin and bad hemoglobin. Both of these type of hemoglobins have 146 amino acids in their primary structure, but they are different in just one amino acid. If you must have glutamic acid available to work like glutamic acid does. If accidentally, instead of glutamic acid, you put valine in, then what's going to happen? That is the real question. And the bottom line is by changing it from glutamic acid to valine, look how much we changed in the shape of these cells. And this isn't a bad case, but not a hugely dramatic case. So where is the recipe for hemoglobin stored? Just to make a connection here, it's the central dogma of modern biology. The recipe is a gene stored in DNA. A gene is a segment of DNA or a section of DNA that contains the nucleotide code for a protein, and the primary structure of proteins is coded into DNA. Oh, then we talked briefly about eggs and collagen. All of these things are things you can go and look back and think about. Interesting questions. Just sort of test yourself. Okay, could end up in a. These could easily end up in a quiz question. Hold on. Okay. Very famous protein, collagen. 40% of the protein in the human body is collagen. It's actually made of, this is a alpha helix. Can you see it? Twisted. This is made of an alpha helix. 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 All three of these are made of alpha helix. And those alpha helixes are wound into a bigger helix. And that structure provides great support and strength for long muscle fibers in, say, the leg. Of course, there's always a connection between structure and function. Here you go. Here's an opportunity for you to answer some basic questions about that. Anyway, and so here's actually the segue into the next part. Okay, segue into the next part. It says, what makes your body develop as a human body while your cat develops as a cat? What makes your kids develop to be like you? How do your cells know what molecules to make and when to do it? For that matter, how do they know how to make the molecules they need to make? Your body needs to contain and use and store lots of information, right? All of these, I mean, it's amazing if you think about it. We start out as a single cell, formed in our mother's oviduct. We are formed by a sperm that carries 23 DNA molecules for humans. And that sperm, that lucky sperm, fertilizes an egg that has 23 DNA molecules in it. That's the human number. 23 plus 23 is 46. That's what we expect. Every normal body cell in our body has 46 DNA molecules. Where did we get them? We got 23 from our mom, and we got 23 from our dad. 23 plus 23 is 46. Anyway, then that single cell, one cell, it starts to divide into 2 cells, 4, 8, 16, 32, 64, 128, 256, et cetera, 50 trillion. But how does it know? How does it know what to do? How does that one cell know how to make a liver? How does that one cell know how to make a brain? How does that one cell know how to make a vegetarian lasagna? No. How does that one cell know how to do all the biological stuff that it needs to do? And the answer is nucleotides and nucleic acids. So this is the last group. Monomer nucleotides. Monomer nucleotides include ATP, GMP, and NADH. Polymer nucleotides are DNA and RNA. I need to jump away from this for a second because there's one other bit of information I'd like to put here if I can. Let's see. Sorry, folks. I always want to tweak these things. So first thing I want to mention, of course, is that nucleotides have always contain 5 different elements, always. Those 5 different elements are carbon, hydrogen, oxygen, nitrogen, phosphorus. I mean, just for the record, carbohydrates contain carbon, hydrogen, and oxygen. Lipids, most lipids, 98% of them are made of just carbon, hydrogen, and oxygen. And how do we tell the difference between a carbohydrate and a lipid? Well, Carbohydrates have lots of oxygen. There's almost a one-to-one relationship between oxygens and carbons. Most carbons in a carbohydrate are actually bonded to an oxygen. Most carbons are bonded to oxygens. Now, in a lipid, it's again only made of carbon, hydrogen, and oxygen. But the number of carbons and oxygens is dramatically different. Remember cholesterol, C27H46O, 27 carbons, 46 hydrogens, 1 oxygen. Okay, so carbon, hydrogen, oxygen in carbohydrates, oxygen's super common, C6H12O6. In lipids, oxygen's much more rare, could be C18H36O or C13H36O2 is probably more what it's going to be. But again, 18 carbons, 2 oxygens, that says oxygen is relatively rare. Now, in proteins, what are the 4 elements that are always found in proteins? Well, let's just for a second take a look at amino acids. Carbon, hydrogen, oxygen, nitrogen. Carbon, hydrogen, oxygen, nitrogen. So when it comes to amino acids and thus proteins, you're going to find lots of carbons, lots of hydrogens, lots of oxygens, or reasonable number of oxygens and nitrogens. Okay, you're going to find them all in. You're going to find CHON in proteins or amino acids, but in nucleotides, you now have phosphorus. You have something called a phosphate group, which is phosphorus to oxygens, and it is part of the big nucleotide molecule. A monomer in the nucleotide group is pretty big, and I'm going to show it to you. Now, monomer nucleotides, what we call monomer nucleotides, include ATP, you've heard of it, GMP, NADH, we'll talk a little bit about all of these. Polymer nucleotides, they're also called nucleic acids. Okay, so polymer nucleotides are sometimes called nucleic acids. They include really famous molecules like DNA and RNA. DNA is a huge molecule. I mean, DNA, an average human DNA molecule is built of 65 million monomers, 65 million. A huge number. Now, an individual nucleotide is made up of these 3 parts. A nitrogenous base. Nitrogenous means full of nitrogen. A base that's full of nitrogen, and the possible bases are adenine, thymine, cytosine, guanine, or uracil. All nucleotides have a 5-carbon sugar. That's what this 5C stands for. And that 5-carbon sugar is either ribose or deoxyribose. And then a nucleotide always has 1 or more of these things called phosphate groups. I'm going to show you what those look like. Okay. Okay, here is a basic nucleotide. Very straightforward basic nucleotide. This is one that you would find in DNA, right? 1, 2. Trying to count the oxygens, and I realize that the information that's here, some of the oxygens have been lost in a dehydration synthesis bond. But anyway, bottom line is that take a look at the parts. Here is the nitrogenous base. This is a base that is, well, full of nitrogen. Look, I see 1, 2, For 5 nitrogen atoms. This is an unusual molecule. It is a ring, 2 rings attached together. This represents double bonds. This particular nitrogenous base, the A, stands for adenine. We'll come back to the different nitrogenous bases. Here is a 5-carbon sugar. In this case, it is ribose. No, in this case, it's deoxyribose. Anyway, so this nitrogen base is attached to a 5-carbon sugar, and that 5-carbon sugar is attached to a phosphate group right here. And phosphate groups, well, there's phosphorus bonded to 1, 2, 3, 4, 5 oxygens. It's forming covalent bond there, and this is called a phosphate group. Nitrogen base, 5-carbon sugar, phosphate. Nitrogen base, 5-carbon sugar, phosphate. Now, does everybody remember what this means up here? CHONP. It doesn't. It stands for elements: carbon, hydrogen, oxygen, nitrogen, phosphorus. Okay. Those elements that are always found in nucleotides. Now, here's a good old ATP, the most famous monomer nucleotide. Now, I got to go back here for a minute because I'm sorry, but I got to just insert something in here. It's important. So let's hope I can do it. No. Functions. Monomer nucleotides. All right, I knew I would have to tweak this, which is why I have not posted it yet. Okay. Down here, I'm going to get rid of this because down here I want to write functions. Come on. Why did it let me paste that in there? Okay, fine. I forgot where I was for a minute. right, that's what I wanted to have here. The functions of monomer nucleotides, right, laid out there. Of course, monomer nucleotides can be used to build polymers like DNAs. I mean, the term monomer right away suggests they could be used to build polymers like DNA. Okay, and secondly, these are super important energy storage molecules. Super important energy storage molecules. And of course, the one I just mentioned was ATP. And I did write right here, used as energy storage and transfer molecules. And I guess that's because in a certain sense, you don't store energy in nucleotide molecules for very long. You don't. Usually for just fractions of a second. It's put in there, then the energy molecule is transferred somewhere and the energy is taken out and it goes back to be recharged. Like my cell phone, which doesn't hold a charge very well. And anytime I'm near a place where there's energy, I plug in my phone charger and try to charge my phone up, because I know that as soon as I leave that, I'm going to take the phone off the charger and then it's going to immediately start using energy and it's going to be discharged. Okay, so just wanted to make a note here. This was something that was in my mind. I'm thinking, I need to mention the functions of monomer nucleotides, and there we go. All right, back to the slideshow. Okay, nice. All right, well, that had to be there. ATP, the most famous monomer nucleotide. I think so. I really do think it's true. So remember that monomer nucleotides have a nitrogen-containing base. The nitrogen-containing base here in ATP is called adenine. Okay, adenine. This is the 5-carbon sugar right here. Okay, it's the in this case, this is ribose, I'm pretty sure. So this is a 5-carbon sugar, and I see 1, 2, 3, 4, but oh no, maybe not. Anyway, this is ribose or deoxyribose. I'm pretty sure it's ribose. And then take a look. Here's one phosphate group, another phosphate group, and another phosphate group. And they mention here that this bond here is a high energy bond, meaning it can store a large amount of chemical bond energy in it. Now look, here's the bottom line. If you're an enzyme and you grab this phosphate and you just rip it off, then this energy in between these bonds, some of this energy is going to be released. Now you want to position the ATP just right so when it releases that energy, it goes right where you want it to go. What you don't want is just to release that energy in a frivolous way. Because remember how energy is. You either use it immediately, you store it long-term or temporarily, or goodbye, it's gone, and you've wasted that energy. So here's a high energy bond. There's a high energy bond here too, but in most of the time in the breaking apart of this molecule, this one doesn't get broken apart. This one gets broken apart all the time. This is where energy can be stored. This is where energy can be released. Okay, so ATP is often referred to as the rechargeable energy battery of the cell. Rechargeable energy battery of the cell. And you know what? It's been over an hour. I need to take another break. If I don't take a break about every hour and stand up and move around, then I'm kind of crippled later. Okay, so I'm just going to escape from this. And I'm going to do something I should have done, which is to look and see if there's any chat. No chat questions. All right. Almost watch the cat there. The sound of smooth jazz means that it's time to take a 10-minute break, okay? All right, get up, stretch, move around a little bit, okay? I'll see you in 10 minutes.
work, Dad?
Just setting up a smart TV.
Just connect to Wi-Fi. You know we should secure our Wi-Fi too, right?
With Cox Panoramic Wi-Fi, securing your network is so simple, even Dad can do it. Learn how at cox.com/panoramic Wi-Fi.
At Speedway, we've always been here to get you what you need when you need it. We're committed to keeping our stores open, clean, and safe, so you can stay fueled and refreshed all summer long. We've got cold drinks for hot days and frozen drinks for even hotter ones, plus energy boosts, quick bites, and pick-me-ups. We're always on your way, and we're always here for you. So no matter what you need, when you stop by, we'll be ready. Now buy any 3 cooler beverages and get 500 bonus Speedy Rewards points.
ATP, the rechargeable energy battery of the cell. All right, I want to go from this current slide, though of course I would be happy to answer any questions that anybody has about anything so far. I better check the chat. No one's chatting at me. Everybody's asleep. It's the middle of the afternoon, and it's summer school. Summer school is notoriously taxing, I think. Notoriously taxing. Oh, thanks, Kendall. I will get you back. I'll get back to you as quickly as I can. All right, so here we go. Let's go back to where I just were. If I can find myself where I am. There I am. I was back at the rechargeable energy battery of the cell. Oh, I'm presenting to everybody. Good. That's a good thing. Rechargeable energy battery of the cell. We're still talking about two things, right? We're talking about monomer nucleotides, which are could be used to build polymer nucleotides. We're going to talk about polymer nucleotides in a minute. And then, but one of the functions of monomer nucleotides is they are energy carriers, energy transfers. You can store energy in them, and that energy then can be transferred. So I got to say, this isn't the first time we've talked about this reaction, because look at these two arrows here. Now, I know this reaction looks weird, but arrow this way, arrow this way. This is the symbol of a reversible reaction. What they're saying here is that here's the charged form of ATP. It has 1, 2, 3 phosphate groups. Here's a high energy bond. Here's a high energy bond. This is the one that's most important to us. Now, we know it's the fully charged form because it is adenosine triphosphate. That's the charged form of the battery. This last phosphate group is attached by a high energy bond. Now, if you need energy, then you're going to take this ATP molecule and you are going to break it down into ADP, which stands for adenosine diphosphate. It's 2 phosphates now, not 3. But where did this phosphate go? Well, here it is. This phosphate was released plus energy to do work. So when an enzyme will come and it will grab this phosphate and it'll rip it off. And when it rips the phosphate off, it doesn't destroy it. Here it is right here. But when it rips it off, the energy that's in this bond, not all of it, but a lot of it, spills out. And that's energy available for use in the cell. To do, what did I do there? Gosh, I did not mean to do that. Oh no, now it's writing down everything I say. Uh-oh. Well, that is kind of interesting, I suppose, but that's not what I want to do. That thing should follow me around all day, and then I will, whatever I say, it'll write it down. It did a pretty good job of writing it down, actually. All right, so if you need energy, you will rip this phosphate group off, releasing this energy, and that energy hopefully be used to do something important in the cell. Of course, once you've ripped that phosphate off, what you have is the uncharged form. ADP stands for adenosine diphosphate. 2 phosphates, not 3, but 2 this time. Why? 1 has been taken off already. So again, if you need energy, then you're going to take ATP, the 3 phosphate form, and you're going to pull 1 phosphate off, release energy, and now you're going to have the 2 phosphate form. But what if you need energy? Sorry, what if you have energy? What if energy appears? And again, energy can appear when you eat a big meal and now you've got glucose, and the glucose goes into your cells. And you know what? The minute glucose goes into a cell, it is broken in half immediately in that cell, and energy spills out. a significant amount of energy spills out. So when energy appears, remember the drill. When energy appears, what do? Well, really, there's only one thing you can do. You either store it, or you use it, or you lose it. Store it, use it, lose it. Those are your three choices. If somebody can think of a fourth choice, I'd be interested in hearing it, but I feel like those are the three big energy choices. So let's say you have energy. It's appeared because of your big lunch. Do you have phosphate groups? Oh, yeah. Trillions and trillions of phosphate groups just waiting there. So you take that energy in that phosphate group, and you're going to attach it right here, and now you're going to have ATP, adenosine triphosphate. This is the charged form of the battery, and this is the discharged form of the battery. And why do I keep going on and on about ATP? It's because most cellular machinery runs on ATP. Like I said before, there's like 80 ATPs worth of energy in a glucose molecule. And that's just way too much energy. I mean, this is just like jet fuel. The cell can't run on it. So ATP is the rechargeable energy battery of the cell. It's a reversible reaction, right? ADP plus P reacts to form ATP. ATP breaks down into P and ADP. If you need energy, you're going to go this way, right? You're going to break down ATP into ADP and P and energy. If you got energy, right, some energy just appeared, well, then you're going to go this way. Because really, this equation I set up here, simplified, here's what it really should look like. Energy plus ADP plus P reacts to form ATP. This energy is now stored in the ATP. But if you need energy, well, then you're going to go just the opposite direction. You're going to take that energy storage molecule, you're going to rip the phosphate group off. There it is. What's left? ADP. What's released? Also energy, which of course our cells need energy to run. So it turns out there's actually three types of bases you can have in nucleotides. We've basically been, no pun intended, we have been talking about mostly about the base adenine, which is a very famous base, no doubt about it. We find it in ATP, for example. We find it in NADH. We find it in DNA. We find it in RNA. But there's 4 different bases you can find in the nucleotides of DNA. And there's 4 bases you find in the nucleotides of RNA. Notice both DNA and RNA have adenine. DNA has thymine, RNA has uracil. Both DNA and RNA have cytosine. Both DNA and RNA have guanine. So, honestly, if you were to look at a molecule and it was a polymer nucleotide molecule, and you saw that it had a T in it, then you would know automatically it must be DNA. If it has a U in it, you would know automatically it must be RNA, okay? So you can tell a little bit that way. In fact, these letters, ATCG, these letters are super famous. And the reason, is there 2 blocks here? Yeah, there is, okay. Pull this block down. These are the letters of the DNA alphabet. And I don't know, I kind of feel like every time I think about these letters, I think about this movie, and it was called GATTACA, the movie. And it was a movie with Uma Thurman and Ethan Hawke. Oh, and I don't know how old it is. I want to say it was 20 years old, about 20 years or so ago. Maybe somebody could Google it for me. It's called Gattaca, the movie. I think it's 2 T's. It's not two T's. I'd like to know that. Somebody Google it out there. And see if you can find out anything about this movie, when it was actually made, and whether I spelled it right. But this movie, Gattaca, was a movie about a company that was manipulating DNA. And I thought it was creative, of course, that they named the company, I think, Gattaca, which is Gattaca, since the alphabet letters that represent nucleotides in DNA are ATCG, GCTA, ACGT. I'm going to escape and see who Googled it. Nobody Googled it. Oh my God. I do know everybody's asleep. Just, know it. Ah, 1997. I already know about it. And I spelled it right. Oh, wow. Look at all the people. Ethan Hawke, Uma Thurman, Jude Law, Ernest Borgnine. Is that guy still alive? Well, 1997. Maybe he was. But anyway, this movie. Okay, I finally found it out. Better be careful what I do here. Okay, so 1997. That's before most of you were even born, huh? No wonder you've never heard of this movie. This is an obscure movie reference here. But it was a movie about a company that manipulated DNA, Gattaca, deliberately. Nobody made a movie about RNA. I don't know what we would call it. But anyway, so, oh, great. I've always, for years when I have thought about the types of bases in DNA, and I think about ATC and G. I think about that movie Gattaca. I don't know if it was a particularly good movie. I don't really remember it that well. But anyway. Okay, very nice, Steve. Here we go. I can make a PowerPoint. Well, sort of. All right. So these are the types of bases. Now, here's the thing. When you make a nucleic acid, you're making it out of monomer nucleotides hooked together. So here's a monomer nucleotide. Here's the nitrogen base adenine, the 5-carbon sugar, and the phosphate group. Nitrogen base, 5-carbon sugar, 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 phosphate group. This part here is made of the sugar and phosphate groups. These, the sort of rungs of the ladder, those are made of the actual nitrogenous base like adenine, thymine, cytosine, guanine, or if this happened to be RNA, it would be uracil instead of thymine. So the nucleotides are hooked together, dehydration synthesis reaction, I'm pretty sure. And then we attach these nitrogenous bases together to make a nucleic acid polymer. Okay, I am going to escape for a minute. I'm going to put down here. I didn't want to underline that. What is this thing? So imagine this is a polymer that's made of 65 million nucleotides long. I mean, that seems amazing to me. Average length of human DNA molecule is 65 million nucleotides. Wow, crazy. Okay. All right. So we were taught here, we're just looking at one side of the molecule. Let's look at DNA. All right. This is a great picture of DNA. And what it shows, number one, is that DNA is a double helix, right? It's kind of like one slinky coiled up with another slinky. How are the slinkies attached together? Right here, this dot, dot, dot. Hopefully that dot, dot, dot reminds you of hydrogen bonding, because it is hydrogen bonding. Adenine forms a hydrogen bond with thymine. Thymine forms hydrogen bonds with adenine. Guanine forms hydrogen bonds with cytosine. Cytosine forms hydrogen bonds with guanine. Adenine with thymine. Thymine with adenine. Guanine with cytosine. Cytosine with guanine. Guanine with cytosine. This is called the DNA base pairing rule. Adenine will always form hydrogen bonds and thereby base pair with thymine. Cytosine will form hydrogen bonds and thus base pair only with guanine. Guanine will only base pair with cytosine. This rule is kind of worth knowing because when we think about DNA replication, which we're going to think about pretty soon, we have to be able to think about how DNA is copied inside of cells for cell reproduction purposes, sexual or asexual. And so anyway, so we've got the same kind of thing here. Here's nitrogen base 5-carbon sugar phosphate. Nitrogen base 5-carbon sugar phosphate, right? Nitrogen base 5-carbon sugar phosphate, and these are strung together. In the case of DNA, of course, it's considered a double-sided, double-stranded molecule, and the two sides are hooked together by hydrogen bonds. Remember, hydrogen bonds are not the strongest bonds, but if you have millions of them, it will create a pretty strong and stable molecule. But it can be damaged. Ultraviolet light can damage DNA. And it damages the hydrogen bonds. So the bottom line is there's things that can damage DNA for sure. But this rule, adenine always base pairs with thymine and cytosine always base pairs with guanine and vice versa, is a pretty good rule. You'll never see guanine base pairing with thymine. And a base pair means we're taking this nitrogenous base and pairing it with this nitrogenous base. Cytosine always base pairs with guanine. Thymine always base pairs with adenine. So a lot of this was about, just talking about basic nucleotides, but I can't resist the urge to shove in interesting information about molecules like DNA that are such important biomolecules. So the sequence of nucleotides contains the information in a DNA molecule. So this piece says A, T, C, G, T. That's the sequence of this piece. A, T, C, G, T. Now, honestly, I can't tell you what information this contains. It's possible that it does contain some actual information that's possible in the DNA perspective, but like it says, you can think of it as a language with only 4 letters. But those letters can be used to create some very long words. Now, again, if this is a piece of DNA, we know automatically, just like this was a piece of DNA, we know automatically because look, thymine, that says DNA. thymine, that says DNA. Thymine, that says DNA. But what kind of information is going to be encoded in this? Well, I can't tell you about every kind of information that's encoded in it. I'm not sure that it is actually known about all the possible kinds of information that can be stored in a DNA molecule. But one piece of information that's definitely stored in the DNA molecule is the recipes for proteins. The recipes for proteins are stored in the DNA molecule. And you already know this. When these recipes are stored in the DNA molecule, they are called genes. So DNA sequences make up genes. A gene is a stretch along a DNA molecule that contains the information to make a protein. Genes determine the primary structure, that is the amino acid sequence of proteins. DNA doesn't act alone. RNA carries the information to where it's used in the cell. DNA stores the information, RNA carries it to where it's used. So very important, very basic DNA stuff. Why do I have two of these? Genes determine the primary structure sequence of proteins. The primary structure determines how the protein will fold and the function it will have. Proteins do everything and make up the entire body, or just about the entire body. I mean, sure, there's water in the body, and that's important in creating structure inside the body for sure. Therefore, genes, I mean DNA, determine what kind of body we'll have and how they function, as well as what your kids will be like. So the DNA inside of our body cells is responsible for, among other things, making sure the right proteins are made at the right place and the right time. So we absolutely have to talk about something that's perfect. I think it's perfect to talk about here. We've already alluded to it. It's called UGG, the central dogma of modern biology. And what's making me say UGG is this dogma, because I don't see how a word like dogma fits into science. If you look up dogma in the dictionary, on Google, whatever, it's going to say dogma is an unquestionable truth. You know, unquestionable truth, which just does not sound like science to me. That sounds like religion to me. And in fact, I'm not really sure why the guy who first referred to this as the central dogma of modern biology, it was Francis Crick, one of the discoverers of the structure and, to one degree or another, the function of DNA. So back in 1958, he called it the central dogma of modern biology. But you know what? When he was asked about it, he realized he'd made a mistake, and he said, I thought dogma meant hypothesis. So what he really should have called it was the central hypothesis of modern biology back in 1958. Okay, well, that was like 20 years ago. And so since then, they have been slicing and dicing and doing lots of experiments. And now there's so much support for this central dogma, central hypothesis, that really it should be called now the central theory of modern biology. But if you want to look it up and study it, and you put the central theory of modern biology, I'm not exactly sure what you would get. Okay, so they do mention central dogma, and so that's at least nice that they mention it. I think that if you wanted to really study it and learn a little bit more about it, you would probably want to go to Central Dogma of Modern Biology, and it will start to explain it. Though I'm going to give you like the simplified version of it, the 5-minute long simplified version of it. And I'm going to tell you that this is a hugely important idea in modern biology. And I'm giving you sort of the simplified version, which says this. Okay, look. DNA is stuck in the nucleus of the cell. We never see DNA outside the nucleus of the cell unless the cell is dividing and basically kind of moving everything around and getting the cell ready to split in two. That's the only time we see it outside the nucleus. So 99% of the cell's life, it is inside the nucleus. That's what these brackets mean. Now, it's stuck there. We know the recipes for proteins are on the DNA, which is stuck in the nucleus. And we know that proteins are manufactured out in the cytoplasm of the cell, outside the nucleus, in the cytoplasm on structures called ribosomes, which are a type of cell organelle. Now, RNA, it's formed in the nucleus, but it leaves the nucleus and goes out into the cytoplasm of the cell to coordinate the production of proteins. And we will very soon talk about how, in this very basic story, the simplified version, there are 3 forms of RNA that all work together to make sure that the proteins are produced. Okay. Now, I also want to mention these terms. When you take DNA and you copy it to make RNA, that's called transcription. So when you copy DNA inside the nucleus to make RNA, it's called transcription. When you allow that RNA to leave the nucleus and move out into the cytoplasm to coordinate protein synthesis, taking the RNA copy and turning and using that information to make proteins. You don't turn the RNA into protein. The RNA doesn't get turned into protein. It is an information molecule that is able to guide the production of proteins outside the nucleus in the cytoplasm. Okay? And, okay. Oh, okay. All right. So just so you can see the central dogma of modern biology, slideshow, current slide, we're back here. You know, again, this is so important, has had such profound impacts in biological thinking and in the world, really. It should be called the central theory of modern biology now. Now, here's the thing. The biotechnology revolution that we've all experienced, and that is making amazing things happen in medicine and et cetera, that has been driven by the central dogma of modern biology. Amazing things can happen when you start using this as a format for understanding the relationship between DNA, RNA, and protein. No doubt about it. Okay, it has formed the biotechnological revolution. Again, just to make sure I connected this right, when DNA is copied to form RNA, it's called transcription. I'll show you what this looks like. When RNA is used to coordinate the production of proteins, it's called translation. Okay, very famous terms in modern biology. So just in a sort of pictorial way, here's a picture I stole off the internet, of course. And here is nice double-stranded DNA. And one thing that happens to DNA all the time is that DNA gets copied and copied and copied. In many cells of our body, the DNA is not being copied, like muscle cells or neurons that are long cells in our body. But a huge number, certainly trillions of cells in our body, they need to do cell division. And so if you're going to do cell division, you have to copy your DNA. And that's called DNA replication. And the enzyme that's responsible for doing it, there's a cohort of enzymes, but one of the main enzymes is this really famous enzyme called DNA polymerase. And its job is to take DNA and copy it over and make identical copies of DNA. It's called DNA polymerase. You know, one of the reasons this is such a famous enzyme is because I see it on TV all the time, right? I see something like this happens in a crime show. They find a dead body. They find some tiny amount of DNA on the body that they think, this is not, maybe this is DNA from the person who killed this person. So maybe they take the person and scrape skin out from under their fingernails, and they think, well, they could have scratched whoever killed them. So anyway, once they have that DNA, they can take that DNA and they can copy it over millions of times. And it's done very, very efficiently because it's guided by DNA polymerase. You know, polymerase. The ACE, of course, means enzyme. The polymer means we're building a polymer. What polymer are we building? DNA. So DNA polymerase is the enzyme that builds DNA. And the reason it's building DNA is because in many cells of the body, like skin cells and mouth lining cells and blood cells, the DNA needs to be replicated constantly. And I'll tell you about that DNA replication. Okay, but when you do transcription, remember transcriptions where you take DNA and you copy it over to make RNA? That process is mainly coordinated by a different enzyme called RNA polymerase, of course. Why? Because it makes RNA. That's its job, to make RNA. And RNA polymerase is the enzyme that will copy RNA. And sorry, I said that wrong. I need to be clearer. RNA polymerase is the enzyme that will copy DNA and form a piece of RNA out of it. Now look, the information on DNA, it's going to be transferred very carefully by RNA polymerase. It's going to be transferred very carefully by RNA polymerase to make a complementary RNA strand from that piece of DNA. Right? It's going to be done super, super carefully. Okay. Now, once we have that strand of RNA, it can leave the nucleus. This is all stuff that happens in the nucleus. But once it's formed, it can leave the nucleus and go out to this organelle called a ribosome. Right? And that ribosome is where translation will occur, which means here it is where RNA is copied over to a protein. Okay, copied over to a protein. Now, think about it this way. DNA is in what I like to call nucleotide language, A's, T's, C's, and G's. RNA, it's in nucleotide language. A's, U's, C's, and G's. No T in RNA, right? A, U, C, G. But it's nucleotide language. We're basically changing from nucleotide language and just rewriting it as nucleotide language. That sounds like transcription to me. We're transcribing the DNA to form RNA. Now, Once we've done that, we've transcribed it, then the next part, this happens out in the cytoplasm, is called translation. And take a look. Here's what's happening here. RNA is written in nucleotide language. But proteins, if you had to think about what language a protein was written in, you kind of think about its monomers, and the monomers that build a protein is amino acids. So a protein, its information, the information that's stored in it is in the form of amino acids. In RNA, the information that's stored in it is in the form of nucleotides. So we're actually changing from nucleotide language to amino acid language, and that makes sense why they're calling it translation. We're translating from nucleotide to protein. Now, actually, I wish I could stick it over here because there's another enzyme that belongs in here, and it's called protein polymerase. Because when you take this information on RNA and you use it to string together amino acids down here, you're going to use it. You're going to use a specific enzyme called a protein polymerase. That makes sense, doesn't it? Protein polymerase. And anyway, protein polymerase is an enzyme that assembles a protein polymer, which is certainly happening here. This is A's, T's, C's, and G's. This is A's, U's, C's, and G's. This is amino acid language. So glycine, glutamic acid, asparagine, serine, lysine, isoleucine. Different language we're translating. Okay, so some just very basic questions that I think would be useful to study for an upcoming quiz. Okay. This PowerPoint is finished for now. I've already renamed it as Chemistry 4 PowerPoint number 3. It is ready to rock and roll, ready to go. Ready for you to look at and study. Where am I? Where am I? No chat questions. Everybody's asleep, huh? That doesn't surprise me. Been lecturing solid for 3+ hours. Oh, except when I was dumping stuff in a wine glass full of cabbage juice. Okay. And your email, I want to remember your email, Kendall. I will see that. So you know what? I think people have stuff to do. They've got an exam to work on. They've got a lab to work on. I think I'm gonna push off this cytology PowerPoint to the very beginning of class tomorrow. I'll get it finished up and posted so people can take a look at it. Okay, because this next one is, we're gonna boom through cytology and cell organelles and the cell theory and that kind of stuff. Okay. Today seems like things went relatively smoothly. I was a little bit, a little bit frozen up at times. But I kind of wish I could see everybody and see their faces. I mean, in a normal classroom, I could look at people and go, "Oh, you don't really understand this, do you? Let me explain it again." But in a virtual format, I don't. So again, one of the very first things I'm going to do is I'm going to try and figure out why students can't toggle to D2L. I'm going to do that, or to my PIMA. I'm going to try and find that out right away. And certainly one of the reasons I'm doing that now is I may not be able to get a hold of anybody after 5 o'clock. But do you have stuff to do? Of course you do. Exam, labs, quizzes. So in normal summer school class, I wouldn't lecture for 4 hours straight. I could, no problem for me, but I would instead at some point in time stop and ask people to work on labs or whatever, right? So I think what that means is that I am stopping the recording now. Stop recording.